Seems right.
Recording?
Yes.
So, mine's pro. We've got like networks of neurons. We've got them doing a little bit of information processing. We've got them maybe doing some basic Hebbian learning, firing together, wiring together, that sort of thing.
Yep.
How do we go from there to something we would actually call a mind? Like a human mind, for instance. First key piece that we want to talk about here is within lifetime learning, and more specifically within lifetime selection pressure. So somewhere in like your brain, or before brains evolved, your network of neurons or a network of whatever's passing information, you want to have some sort of mechanism that's going to reinforce changes in response to good stuff happening, whatever that means. So for instance, if like the organism gets some food, then you want to somehow reinforce whatever stuff led to that food happening. If the organism has some sort of high stress event, like being bitten, you want to, being bitten in a bad way, you want to somehow negatively reinforce whatever led to that.
Okay. Although you have credit assignment problems.
Oh yeah, you got hella credit assignment problems. No question about that. And like indeed, looking at how humans act, to a large extent, we just don't solve those credit assignment problems. Right? Like we're just kind of mediocre at it. The main point here is that we're going to end up with dynamics similar to what was going on with evolution, right? With selection pressure, but occurring within lifetime. And that's sort of the main thing that we're going to use as a foundation for the next several pieces of talking about how minds work, right? So like you got a baby, pops into the world, there's some amount that's sort of hard-coded in its brain. It's got a little bit of structure just laid down by patterning.
Yep.
But like most of the what's make it into a mind is going to come along after that. Mostly it's going to be learning things in real time via some sort of feedback mechanism. Make sense?
Yep.
So that's going to be most of our explanations are going to be about like there's some sort of selection pressure here within lifetime. All right, next piece is going to be the horribly named neuron picture, in which I draw a picture that looks like a neuron and is not at all a neuron.
Okay.
So be prepared for that. So the idea is we've got this sort of ball-shaped bit in the middle with these little two-dimensional doodads coming off of it. So these are like little flatter pieces.
Yeah.
And then coming off of those, we've got these little one-dimensional dudes. And what this picture is actually supposed to represent is some sort of low-loss part of a loss landscape. We've got, let's imagine this for a moment for a neural net of the sort that we put on computers as opposed to the sort we keep in our skulls. You could imagine that this picture lives within parameter space. So like here's the value of parameter 1, here's the value of parameter 2. Coming out of the board we have parameter 3, and there's like, let's say, how many parameters does GPT-4 have? Like 60 billion or something? I don't actually know the numbers on these exactly.
I don't think anyone knows. I think it's proprietary.
Okay, well, something somewhere in the like a billion to a trillion range number of parameters, right?
Yeah.
And this picture is showing where the loss on this training set is low. So like out here, loss is pretty high. Once you get down here, it's like getting pretty low. And this isn't like exactly minimum probably as you get more towards in here, where like all of the points are low, the parts more towards the middle are going to be a little bit lower, but this is where it's like reasonably low. So if you start training the thing, it's going to sort of, start at some random point and pretty quickly head towards whatever the nearest point on the low loss landscape is. So probably it'll like zoom into there. And then over time, it's sort of going to drift towards this middle bit. And there's two reasons it's drifting towards the middle bit. First, there's entropic pressure. If it gets from this sort of one-dimensional area into the two-dimensional area, it's going to stay in the two-dimensional area, not go back.
What do you mean one-dimensional versus two-dimensional?
So this guy is sort of like a sort of long strand of points that all have low loss.
Yeah.
Whereas this is like a sort of plane of points that have low loss.
Okay.
Right? And in here you have this whole ball of points that have low loss.
Okay. Is there some claim that this is what the loss landscape looks like?
Yes, and I'm going to talk about why we would think that in a minute.
Okay.
Right. So if you just like initialize at a random point, you sort of quickly zip into whatever the closest point is, and then you'll naturally drift towards higher dimensional parts of the low loss landscape. For two reasons. First reason is entropic. There's just like more points on the interior here.
Okay.
So like if you're sort of wandering around in this ball, you're usually not going to accidentally wander out to this tiny two-dimensional chunk, right?
Yeah.
And if you're wandering around in this tiny dimensional chunk, you're usually not going to accidentally wander out into a little one-dimensional chunk, right? You sort of have to hit it just right for that to happen.
Okay.
Then the second reason is just that there's probably a little bit of a gradient still. So like you would expect that in the middle of a bunch of chunks, a bunch of points that are all getting low loss, you can probably get even a little bit lower.
But these are all of the pink here is areas that have close to the same loss?
Yeah, exactly.
Close to the same low loss?
Lowish.
Okay.
Yeah, that's right.
So it's almost like an indifference curve.
Yes.
But
allowing for a little
with some blur.
Yeah, exactly.
Okay. I have no idea why the loss landscape would have this shape.
Yeah, that's what we're about to talk about.
Okay.
So why would the lost landscape have this shape? Well, think about what it means when we're right here. What it means when we're right here is that we've got some sort of behavior, like our parameters have locked in some sort of behavior for our net that requires almost all of the parameters to have like their values at basically this value. There's maybe like this 1 degree of freedom in there that wouldn't change things that much, but most of the parameters sort of have to be locked into this value. Right? So we've got a strategy that's like not very robust to changes in parameters in most directions.
Yeah.
Whereas in here, it's got more degrees of freedom. Right? We can sort of change in more ways without just like totally destroying our loss.
Okay.
So in some sense, what these are sort of not very robust mechanisms, or not mechanisms that aren't very robust to changes in like a few of the parameters.
What are we imagining? Is this like an image classifier? What
Sure.
is
You
this?
can an image classifier is a fine example.
Okay, and all of the points in this space represent possible policies, or possible like sets of weights.
Yep.
And there are some that are very brittle.
Yep.
They're so brittle that if you change one of the weights, it breaks the whole thing.
Mm-hmm.
Okay, which that doesn't seem intuitively true to me. But
we don't usually find usually when we train these things, we end up at points that are not that brittle, right?
Yeah, and also the way a neural net works, there's like feature detection, such that like we're not doing so good at mechanistic interpretability, but sort of in principle, you're like, I can see this part is finding the edges, and then it passes it up to,
that's right.
to this thing, and that doesn't.
We're
That's not
gonna
compatible.
get to that part in a minute, but that is compatible with this picture.
Well, it's not compatible with a picture where if you change one neuron, or the weight of one unit in your neural net, the whole thing breaks.
It's not that the whole net breaks; it's that your loss goes up a lot. So like it could be
Okay.
that you've got this fairly modular structure where one part of the net is specializing in one thing, passes some sort of clear signals to the next thing, but then if you break that next thing, your loss still gets destroyed.
Aren't the things on the one-dimensional strands places where if you change any of the weights, not just some important weights, but if you change any of the weights, it breaks the whole neural network?
Roughly, yes.
With the exception of the axis along which the strand is.
Yeah, that's basically right. So like if we have, let's say we have a 2-layer net, and like here it's computing a bunch of features, then it uses those features to classify an image, right? This could be very robust or not very robust. It could be that like if I change any weight in here, that fucks up one of my features, and then everything is screwed afterwards.
Yeah.
It could be that if I change one weight in here, suddenly it just completely throws off my calculation, my decision, right?
Yeah.
Or it could be the other way around. It could be that these are both fairly robust. So the question of like how much it's breaking stuff up doesn't quite line up perfectly with the picture of like how robust is it with respect to weight changes. Although those two are related, we're going to get to that.
I maybe missed that. How modular your neural net is doesn't relate to how robust it is.
It does, but like it's non-trivial. It's not in exactly the way you were picturing.
Okay. Okay, so you claim that there are a bunch of ways that you can get low loss that are extremely brittle. It's not most of them. Most of the mass of this odd shape is going to be in the center. Yeah, another thing here is it's not obvious to me that there should be only one center. It seems like there might be multiple
Yes, there
clusters.
could be another dude like this over here.
Yeah. And they're like, in fact, I would imagine there are lots of them in the sense that when you're training a neural net, I imagine there's path dependent stuff where like you're going to need module A and module B, but it doesn't matter whether or not module A is on the left side and module B is on the right side, or vice versa.
Yep, that's right.
And there's not like there's not a bridge between those where you get low loss, as you like gradually swap them. You're sort of like into.
Interestingly, in the case of today's neural nets, there might be a bridge there. This is the thing about Bayesian interpolation.
Okay.
But that's kind of not particularly central to the current thing.
All right. Well, no, there's a lot to follow up here. Follow up on here. Okay, but you're like there is. Most of the things you can find are not super brittle, but there are super brittle things out there, and also the brittle things have connections to the less like there's a loss. There's like
they'll tend to be connected up, so you can if you like first find a brittle thing, you'll tend to sort of drift towards the less brittle things.
Are there reasons why there aren't brittle islands?
That's mostly just a matter of like in high dimensions, there's usually a direction you can go.
Okay.
But it may be that there's some. It'd be hard to tell.
Okay, so well, also getting lower loss doesn't necessarily mean that your neural network is more robust to changing the weights.
Correct.
So it might there's some way you can go in the sense of there's like a gradient in the loss.
Yes.
That doesn't mean necessarily that there's a gradient toward more robustness.
Correct. Although we would expect these two to be related, and that's this part's important. Conceptually, if you have very robust lowish loss, then that means you have a bunch of leftover degrees of freedom to play with. And so you can potentially use those degrees of freedom to get like slightly lower loss, right? So like if you're in this sphere in the middle here, you've got several degrees of freedom to play with to maybe get lower loss. Whereas if you're out here, you don't have a bunch of degrees of freedom to play with. It took all the degrees of freedom you had just to get on that line in the first place. And so it's going to be harder to like use those to achieve a lower loss.
Okay, and so every way that you can improve your loss locally is going to entail if there's improvement to be had, it has to be along a dimension in which you have degrees of freedom.
Exactly.
And
so if you have more degrees of freedom, then it's a lot more likely that you can achieve an improvement.
Okay. I guess I follow. I'm still like, well, I don't know. John is asserting that this is how the lost landscape looks, and I'm like,
let's talk about some of the kinds of evidence we have for this and like why, like where this model comes from.
Okay.
So this model comes largely from grokking. Actually, let me back up this stuff. As we move from here to here, one thing that's happening is we're learning a more compressed or more compressible model. Because there's lots of degrees of freedom here, that means that we're using fewer of the parameters to like actually encode whatever policy it is we're encoding. Does that make sense?
We're using fewer of the parameters to encode the policy. Yes. Some of the parameters could be doing whatever. Yeah, okay.
Yeah. And that's actually like the thing that I want to be the main takeaway of this picture is this sort of, insofar as this picture is correct, there's a pressure towards more compressed or more compressible policies. There's compression pressure. Even though you're in this giant high-dimensional space, you're still by default going to be selecting for simple policies in the sense that they're like policies that can be compressed or compressed. Right, back to grokking. So the way this story plays out in the case of grokking is initially you start training the thing, it's effectively memorizing a bunch of data points, right?
Yeah.
So it's memorizing a bunch of stuff. That ends up here. You're using a lot of parameters to sort of memorize those data points, quote unquote. Then as it learns like more generalizable rules, it's moving towards using fewer of the parameters, right? It has more degrees of freedom, even though the loss, the training loss is staying at like a pretty similar level. It's only going down a little bit. And I have actually seen people do the check where like you check what's the shape of the lost landscape around like the point early in training before grokking happens, and points later on, and you can indeed check that they're in sort of higher and higher, like the shape roughly does look like this over time. As the thing is grokking, it has sort of more and more directions it can move in without changing the loss too much or without getting a much higher loss.
Okay.
So it is a thing we can empirically check, and people have like
Okay.
empirical tests on this in at least some networks.
As networks generalize networks are starting out memorizing.
Mhm.
As they generalize, there's more degrees of freedom in there's more degrees of freedom in the sense that you can go in and artificially sabotage any neuron, and that impacts the loss less to a lesser degree.
Yep, that's the right idea.
Okay.
Or any weight, more specifically than any neuron.
Yeah. All right.
So that's the story.
All right. So the tendrils are, I memorized a bunch of data.
Yep.
And the thing in the middle is a cluster of a bunch of possible representations that are contiguous with each other that represent generalizations
Like
of.
compress it more.
Yeah.
not just memorizing the data. And to be clear, that's not like the only possible way you could get a picture like this, but that's sort of the prototypical picture to have in mind.
Okay.
So here you're doing something that's like it's like encoding a policy, but it's not compressing much. And as you get in here, you're doing more and more compression.
Okay.
Go with that?
Yep.
All right, cool. So again, that's going to be a foundational piece for the rest of our stories of how minds work. Is we've got this within lifetime learning, and then on top of that, we've got something like this, where that's these sort of selection pressures, whatever selection is being run on it. In this case, in the case of like artificial neural networks, it'd be SGD. That selection pressure is going to be selecting for compression or compressibility in sort of this way. Like if you think about it, it's a much more general phenomenon than just artificial neural networks. It's this general thing of like, if you have a better compression of the policy, that's going to leave more of your parameters free to vary. And therefore this like more compressible policy is going to take up a bigger chunk of your parameter space.
Okay.
You could
Smaller chunk of your parameter space.
no, like bigger. Like this wall takes up a bigger chunk than this tendril.
The tendrils are using all of the parameters to have the real representation.
Yep. And because of that, they have few parameters left, so they don't fill very much space. Because you can't move.
Got it. Right. Right. Using more of your parameters means that you have less parameter space to maneuver in.
Exactly. And we could say the same thing in other contexts, other kinds of processes that are doing search or selection or whatever. Like for instance, when we're talking about genomes and natural selection, we could tell a similar story where like if a genome is encoding the same policy in a way that uses fewer base pairs, or leaves more base pairs free to vary, like it's more robust to changing different base pairs, then it's going to take up a sort of larger basin in the space, and therefore be more likely to be found. Things will tend to drift towards it over time, that sort of thing.
Yeah.
So there's this pressure towards compression whenever you have like a selection process in a high-dimensional space. And that pressure towards compression in turn becomes a pressure towards generalizability, because like rules that generalize well are going to typically be able to compress things better.
Yeah, okay. Compression and generalization go together.
Compression and generalization go together, and compression happens by default under selection pressure on something high-dimensional. Oh, I should get a picture of this. So now, as we go through like the next few pieces of how minds work, a lot of our explanations are going to ground out in, well, X happens because it allows for better compression, right?
Okay.
To modularity. We briefly brought this up earlier, but now it's time to go into more depth. So, why modularity? Why would we expect minds to have like, chunks that are specialized in different things that are sort of like talking to each other, right? This sort of architecture. Thoughts? Why would we expect that?
So, evolved systems sort of push against modularity.
Because?
Everything has to be a continue, a continue or one mutation away from something that works. And so you can't add in new systems, new subsystems all at once. You have some existing subsystem, and then it incrementally develops some additional function, and then everything's all tangled up.
Good guess. Turns out to be wrong in practice.
How so?
So first of all, if you have you seen the picture of a fruit fly where you do a one gene knockout and then its antenna turn into legs? So it's like legs coming off of its head.
Yes.
That doesn't happen in non-modular systems, right? Like if you've got a non-modular system and you go like knock out one gene, suddenly you've got like a sort of confused ball of cells, right? If you do a one knockout gene and suddenly your one like recognizable part of the system became like a different recognizable part of the system, that's telling you, look, there's like this one thing that's controlling whether this thing is an antenna or a leg. That's extremely strong modularity. And we see this like all the time in biological systems. You do these one gene knockouts and they have like pretty specific impacts on pretty specific functions, right? That's very strong evidence of like these systems are actually extremely modular, despite like your argument sounds right. Like somehow these systems are ending up extremely modular, despite the fact that they had to evolve by like systems sort of randomly having bits added onto them, right?
Yeah.
So why the hell does that happen?
I mean, so it's certainly easier for a human, like if I'm looking at some software, it's just, why should you make software modular? It's so I can tell what's going on with the software.
Evolution notoriously not optimized for that.
Right.
But yeah.
Also, similarly, if I have a machine and it's modular, that's helpful because it means that I can replace individual components.
There we go. Now we're getting to some.
Well, I can't really replace individual components of mine, or maybe not. Maybe I want to update them one at a time.
All right.
I don't think that's.
You're definitely getting in the right zone here.
Okay, one reason to have modularity is if you have function calls that you want to reuse.
There we go. That's a good one. Yep.
If there's a like, I don't even know what kinds of function calls there would be, like an optimize, find the minimum of function. Having that be discrete and callable from like the global namespace is pretty helpful, because otherwise you would need to relearn it multiple times over.
Bingo. Yeah. So I'm gonna do things in a slightly different order than that. Let's go back to our example of like, why would you have internal compartments in a cell, or why would you have two different cells specializing in different things, right? Yeah. Why is it useful to have that boundary there? Well, because it's like keeping this stuff out here and that stuff in there, so we can have different conditions going on. They can specialize in different things. That's modularity in a nutshell. Is there has to be some sort of not necessarily physical, but some sort of boundary between the two that's sort of like keeping the inside stuff in, the outside stuff out, so the outside stuff isn't interfering too much with the inside stuff. So this module can sort of do the same thing under lots of different external conditions. That in turn is something you need in order to be able to have reuse, right? Like if this chunk, this module, is doing something completely different whenever the external conditions change a little bit,
yeah,
then reuse is just not going to work, right? Because the external, something is always going to be changing externally. So reuse sort of needs some kind of modularity. And then in turn, insofar as compression is selecting for reuse, compression is going to select for modularity.
use requires modularity. I mean, I could do a bunch of learning every time I reuse something.
Sounds expensive.
Yeah, well, that's fine.
Guess that is what babies do. Or rather, what humans do. Like every time you get a new baby, it has to relearn all the stuff.
Yeah. Like, one model is you have a bunch of modules that do like pretty crisp things.
Yep.
But you still need to figure out how to chain them together.
Mm-hmm.
And
right.
chaining them together seems like it requires its own reinforcement learning or something similar.
Yes. And in fact, you've already skipped one of the hard steps there, which is we're saying that these modules are like doing a predictable thing. But that's sort of starting to build some kind of semantics or meaning into what the modules are doing. So like maybe, it's a good example here. Let's say I've got a gearbox.
Yeah.
Right? This literally has box right there in the name, great little module.
Okay.
It's nice and sealed off from the outside.
Yeah.
And I can say like, well, that's doing the same thing in lots of different external situations, right? But what does it mean for this gearbox to be doing the same thing when I have it hooked up to a wheel and a crank as when I have it hooked up to, I don't know, an engine and a turbo? Like, what does it mean that it's doing the same thing in these two situations?
Well, it has the same output behavior.
There you go. It has the same input-output behavior. Now, so in saying that it has the same input-output behavior, we've done this like very large step where we've identified what the inputs are, what the outputs are, or at least what the input-outputs are. Maybe there's some sort of equilibrium where there's not really a distinction between the two.
Yeah.
But then crucially, we've said, all right, nothing else is going in and out of this system. The input-output relationship is staying the same regardless of whatever else is going on around it.
Yeah. I mean, there's a different thing that happens with neural nets where you might take, well, I guess maybe that fucks a bit. You might train a neural net. Like you train a language model to do something.
Mm-hmm.
And then you like plop your language model into like some larger edifice that like it gets queried and then it does arithmetic and there's like a outer reinforcement learning loop for like when it is successfully solving some problems.
Yep.
And you're doing backprop through the language model so that it's updating, and then also you put it back and periodically put it in the original language model task. And so it's like if you put it in a bunch of different environments, it will have to learn to do all of them.
Yep.
And this is, it might not have, it will learn idiosyncratic stuff depending on the context.
Mm-hmm.
Like you have a language model and you make it play a video game character and it gets rewarded for playing the video game well.
Yep.
And also you have it be hooked up to ChatGPT and the raters rate it for being a helpful, harmless assistant or whatever, and then so it has to be both a helpful, harmless assistant and also a good video game player. And these don't have the same input-output behavior. You've just trained one thing to be flexible to different contexts.
Mm-hmm.
I'm not even sure I would call this modular. It's certainly not like modular in a crisp way. It's just You're sort of reusing the same machinery.
Yeah. So the way I would word the thing I think you're trying to gesture at is there is a module here in the sense that like there's a fixed I/O behavior, right? And then like regardless of whatever stuff in the environment is going on, it's still going to have the same I/O behavior. But that I/O relationship no longer has a clear semantics to it. Like we can no longer easily interpret it as like this I/O behavior is trying to be helpful, or this I/O behavior is trying to play this video game, or this I/O behavior is like doing X.
Or even like we're going to give it a prompt, and the prompt describes what we like what the input is not necessarily the same type signature it's not the same semantics. Does not have the same semantic type signature, even if it is.
It is going to be like of the same type.
Yeah, that's right.
It has to be, but we're interpreting it differently.
Yes, it's interpreting it differently.
Potentially, yeah.
Yeah, I don't know if this is a tangent.
No, this is extremely relevant here.
Okay.
So there's the way humans think about like modules in a modular system. There's multiple separate things going on. And one of the things going on is just like the thing that we've been talking about here so far, this like there's fixed I/O, there's some sort of boundary that's like preventing anything else in the environment from messing with the I/O relationship, right?
Yeah.
And that's sort of the simplest notion of a module, what modularity is. But then on top of then there's like a more involved notion of what a module is, where like it has a function, there's some sort of semantics assigned to it. We're interpreting it as doing a specific thing. And that's an additional thing on top of that I/O behavior that like even like some things that are modules in the first sense won't be modules in the second sense. Like that's important.
Okay.
And why would that be important? Well, one big reason why that's important is, like you said, there's somehow these modules have to be wired together. The broader system has to be making some sort of decisions about when to use the module.
Yep.
And that, like, how you interpret the module, how you interpret that I/O behavior, is what's going to steer when you're choosing to use it, what things you're choosing to pass in and out of it.
Yep. Okay. But there's a high level point. First high level point is that there's pressure for modularity because that allows for reuse.
Yes.
Okay.
And both of those things were relevant to reuse.
Yeah.
Like reuse requires that like it's not going to have totally different I/O behavior when the exterior conditions change a little, and B, reuse requires that like you have some idea of when you should be reusing it. It's going to be helpful to reuse.
Right. There's some outer process that is deciding when to, or I mean, it might be doing search. Like it might just be trying a bunch of stuff.
True. Yeah, that's a possibility.
In fact, my guess is that's what human brain like.
That we're going to get to in a bit.
Okay. Okay.
All right, so for right now, we're mostly going to be talking about, when we're talking about modularity, I'm talking about it just in terms of the first thing.
Yeah.
Semantics is a more complicated thing that we're going to get to a little later on when we get to search type stuff.
Yeah.
So, again, the big idea here was selection by default selects for compression when you're doing like any sort of search in a high-dimensional space. And then second, compression selects for modularity insofar as it's selecting for reusability. I want to do that right now. No, we're going to skip that part for right now. All right, so that was modularity. Next piece is going to be scarce channels versus scarce boundaries. So there's a sort of duality between how easy it is to pass information in a system and how easy it is to form modules. Does that make any intuitive sense?
Yeah, the more you pass information between elements of the system, the less modular they are.
There you go.
And vice versa.
There you go.
The more modular something is, that means that there's information bottlenecks between them.
Exactly. And this...
Or information ABIs. You could pass a lot of information, but have it be tightly formatted.
Hold that.
Okay.
So that's the right idea. Think about it. So, and here I'm going to put it in context of like we're doing some sort of selection process on a system. So think like training a neural net, or like within lifetime learning of our brain, or maybe even evolution. So our system is going to have this sort of default state where there's a bunch of different parts, right? And they're all interacting. And then, just like you were saying, there's going to be this duality between like, let's make this 2 pictures. If there's, lots and lots of connections here, then, it's very, very easy for information to flow from one place to another.
Yep.
But there's not a lot of modules.
Yep.
So if your system sort of by default looks like this, then information channels are cheap. You need relatively few bits of optimization to form a channel. But modularity is expensive. It takes a lot of optimization. You have to remove a lot of these arrows in order to get a good module.
Yeah.
Conversely, in this system, modules are cheap.
No information.
Channels are expensive.
Yeah.
Now, big question: which of these, are in a sort of typical system that we would be running some sort of search process over? Are we probably closer to this picture, or are we probably closer to that picture?
A typical system that we're running a search process over.
So, like a developing brain or a neural net that's being trained, something like that.
I mean, neural nets are fully connected.
Not usually, but I don't think the difference is super load bearing here.
Neural nets are, I guess convolutional neural nets aren't.
Most neural nets aren't.
Well, yeah. So I'll observe. All right, most neural nets are not fully connected. Humans start out with a bunch of connections and then prune them over time.
Mm-hmm.
I don't have a good take on which direction it's easier to go from. If you don't have any channels, you can't do anything.
Hard to pass a gradient back.
Right. So maybe in principle it's easier to start with lots of channels and then prune them. But I'm not that confident about that.
So here's the claim I'll make. So first, I think a sort of intuitively natural hypothesis is that systems tend to be like this, right?
Yeah.
Like there's a big mess of connections. And first thing I'm going to claim is that actually when there's a big mess of connections, more often it's like this.
Okay.
Counterintuitively. And it's because of chaos. Because of the chaos-like phenomena that we discussed earlier on. Which is if you have a whole bunch of different things feeding in everywhere, then you need information about a whole bunch of different things in order to make any predictions about that guy. So as with chaos, in some sense, as long as you have some uncertainty over some stuff somewhere, it sort of rapidly wipes out your information downstream.
I mean, there could be a power law in how much impact each
Correct. Yeah. So
each node has.
in order to get a situation where, so first of all, this means like there's sort of a limit to how much you can be in this picture at all. Because like if there's no connections, you're in this picture.
Yeah.
If there's too many connections, then you get a chaos-like thing, and you're once again in this picture. So in order to actually have good information flow, you have to sort of be in an intermediate state where like there's not too tangled of a mess of connections here. There's not too many going on, but it's sort of like at a happy optimum where lots of information can flow.
Okay.
So insofar as we buy that claim, and I will say that's like one of the lower confidence claims in this whole run through, but insofar as we buy that claim, the natural conclusion would be modules are relatively cheap, channels are relatively expensive. So the like way we would expect to see things develop in these systems is that like as you're training the thing, or as the thing is evolving or whatever, it tends to evolve new channels over time, new information channels. So for instance, if you look at evolution of organisms, you might expect that over time they're evolving more and more new information channels to like pass information between different catalysts, or between different parts of an organism's body, or things along those lines. Or within a mind, you might expect that the mind is sort of gaining new information channels over time to like, connect this idea to that idea, or to or new concepts that will like carry information between different things.
Between different tightly connected modules.
Not necessarily, even loosely connected modules.
Okay. Alright, I think I should summarize that. Although I should maybe take a nap.
Yeah, okay. Can summarize that, and then we can break for now.
Yeah. How, I'm imagining we're like maybe 2/3 of the way through. Is that a good estimate?
Let me see.
Are we mostly done?
I would
Not even
say
close?
we are a bit more than, so assuming we go through minds and don't go all the way on to like societies and larger economic structures, assuming we stop at minds, I would say we're about 75%,
Okay.
maybe 80.
Cool. It's helpful to know how I should conserve my
I support napping into it.
alright. There are a bunch of things that are... Alright, John claims that minds are very modular. Claims that organisms are very modular. You can tell because sometimes you get a leg that comes out of a head instead of an antenna. And you basically need that kind of modularity because you want to call the same code multiple times. You want to be able to reuse things instead of need to independently reinvent things every time. This is true of organisms. This is true of the development of the bodies of organisms, and it's true of the development of minds of organisms.
Mm-hmm.
And if you have a bunch of nodes that are all connected with each other, the whole thing ends up, any particular node in that structure ends up unpredictable.
Mm-hmm.
Because yeah, I guess I'm not sure, is that... Seems like it could be the case that you have a node that's connected, Well, okay, you have a node that's connected to 1,000 other nodes, and each of those is connected to 1,000 other nodes.
Yep.
And then you want to know what's going to happen, like 20 time steps down the line, and you're not going to be able to predict that well because that's going to depend on, like a lot of significant digits of a bunch of nodes.
Yep.
Is that a problem though? Why do I need to be able to predict which neurons will be active?
So what that means is that there's not actually any information passing from A to B. It gets wiped out by noise.
Within some number of time steps.
Well, steps. Not
Yeah.
really a notion of time here anymore, but yeah.
Right. Okay. So the more
So you can, in other words, you can get modules in some sense induced by noise rather than by like physical isolation.
yeah. Okay. All right. So if things are very unpredictable and very noisy, then nodes are just like not in fact communicating very much with nodes. Some steps down the line.
Right.
It's not necessarily modularity because it can be patchy. It could be the case that every like a module has a boundary around it, and where it's clear what's inside the module and what's outside the module, as opposed to having just like a window and you're like everything that's within two steps from this neuron is communicates with it non-noisily, and then it falls off quickly beyond 2 steps, which is not a module per se. It's just
I would still call that a module. Like it's perfectly fair to have a module that has a boundary that doesn't like cleanly map to a physical boundary.
I mean, also this means that the modules will overlap with each other.
Yeah, that's possible. Although there's like, you have to be careful in what sense they overlap. Like they can sort of physically overlap with each other without necessarily logically overlapping with each other. Like as long as the I/O behavior of one is decoupled from the I/O behavior of the other, then they're still like modular.
How could they could physically overlap? Input output behavior of one of them don't, if they physically overlap.
Yeah.
If they physically overlap, the input output behavior of one of them, it seems like they have to be related to each other somehow. There's like some of the computations are shared.
Yeah, so for example, we have algorithms that can do like matrix vector multiplication of the same matrix against a whole bunch of vectors at once faster than it can do matrix vector multiplication against like one vector at a time. So you can imagine someone takes like a whole bunch of vectors from different users that all want their vectors multiplied by the same matrix and is like, okay, I'm gonna take all these separate vectors and like stack them together and do the matrix multiplication on all of them at once, so it's a bit more computationally efficient.
Yeah.
But this is still going to, the I/O behavior is still going to behave as though I was just doing each of those separately.
Yeah.
And like that could be a useful thing.
Okay, I'm not sure that I follow how those are the same situation, but I think I'm gonna take a nap now.
Why is this it? You should pause the recording first.
Yeah. All right, I'll be back in 40 minutes or an hour,
Cool.
something
Sounds
like
good.
that.